Somewhere out beyond the last planet, a machine about the size of a small car is moving through the dark at more than 60,000 kilometers an hour. It has been doing that for 48 years. It is now more than 25 billion kilometers from the building where it was assembled, far enough away that a message from it takes close to 23 hours to arrive, and an answer takes another 23 hours to get back. In November of this year, it will pass a threshold no object built by human beings has ever reached. It will be one full light day from Earth. It was designed to last 5 years. In the late summer of 2012, an instrument on board that machine began to register something. The instrument was never meant to do the job it was doing. It had been pressed into service because the instrument that was supposed to do that job had died 32 years earlier, somewhere past Saturn, and had never been repaired and never could be. What this substitute instrument was reporting, in a signal so faint it barely rose above its own electrical noise, was that the material around the spacecraft had become 40 times denser than it had been the month before. Not thinner, denser. It took the science team more than a year to agree on what that meant. 2 instruments, both of them working perfectly, were telling different stories about where the spacecraft was and about what, exactly, it had just crossed. Hello, and welcome to Sidereal. Tonight we are going to spend some time with the 2 Voyager probes, and with the region they have spent the last 14 years measuring the outer boundary of the Sun's influence and whatever it is that lies immediately beyond it. Before we begin, if this kind of slow exploration is useful to you, for sleep or for winding down at the end of the day, a like or a subscribe genuinely helps this channel reach the people it was made for. And I am always curious where you are listening from. Leave your location and the time in the comments. Here is the question I want to carry through tonight. When you leave the solar system, what is it that you actually leave? Not where the line gets drawn on a diagram in a textbook. What is physically there? And what changes when you pass through it? Voyager is the only object that has ever gone and reported back. What it reported does not match the picture I was taught. That mismatch is the story. Let's begin. The 2 Voyager spacecraft are identical, and they are strange objects to look at. Each one weighs about 825 kilograms, roughly the mass of a small car, which is where that comparison comes from. The dominant feature is a dish antenna 3.7 meters across, pointed permanently back toward the Sun. Behind the dish sits a 10-sided aluminium ring, about half a meter tall, containing the electronics. From that ring, 3 booms extend outward at odd angles, so that the whole thing looks less like a vehicle than like something that has partly unfolded and then stopped. One boom carries the science instruments. Another, 13 meters long and made of a woven fiberglass so light that the whole assembly weighs about 2.5 kilograms, carries the magnetometers. That boom is long for a specific reason. The spacecraft generates its own magnetic field from its own electronics, and if you want to measure the extremely faint fields between the planets, you have to get your sensor as far away from your own machine as you reasonably can. So they built a mast the length of a bus, folded it into a canister 30 centimeters deep, and let it spring out once the spacecraft was clear of the launch vehicle. The 3rd boom carries the power supply, and the power supply is the reason any of this is still happening. There are no solar panels on Voyager. At Jupiter, sunlight is already down to about 4% of what it is at Earth, and beyond that, it becomes useless. So each spacecraft carries 3 radioisotope thermoelectric generators. Inside each one is plutonium-238, in the form of a ceramic oxide, decaying steadily and giving off heat. That heat passes through a bank of thermocouples, pairs of dissimilar materials that produce a small voltage when one end is hot and the other is cold. No moving parts, nothing to wear out, nothing to jam. At launch, the 3 generators together produced 470 watts. That is not very much. It is roughly what a domestic toaster draws, and out of that budget the spacecraft had to run its computers, its heaters, its radio, its instruments, and the motors that turn its scan platform. The computers are the part that most people find hard to sit with. There are 3 of them on board, each doubled for redundancy. One that receives and executes commands, one that formats and handles science data, and one that manages the spacecraft's orientation. Between all of them, the total memory available is 69.6 kilobytes. A single photograph taken on a modern phone is several thousand times larger than the entire memory of the spacecraft. There is a tape recorder on board, an 8-track digital tape recorder with a movable head because in 1977, magnetic tape was the only practical way to buffer data faster than the radio could send it. The radio transmitter puts out 23 watts. That is about the same as the bulb inside a refrigerator. By the time that signal has spread across 25 billion kilometers and arrived at Earth, the power collected by a 70-meter dish antenna is roughly 1/10 million billionth of a watt. To detect it at all, the receiving stations have to cool their amplifiers to within a few degrees of absolute zero, so that the thermal noise of their own electronics does not drown the message. Those receiving stations are the Deep Space Network, 3 complexes, spaced roughly a third of the way around the planet from each other, at Goldstone in the California desert, near Madrid in Spain, and outside Canberra in Australia. As the Earth turns, each one in turn comes into view of the spacecraft, and each one in turn listens. There is a detail about Canberra worth stating plainly. Voyager 2, on its way out of the solar system, was deflected south by its encounter with Neptune, and it has been travelling below the plane of the planets ever since. It sits so far south in the sky that only the Canberra complex can transmit to it. Not preferentially, only. There is exactly one antenna on Earth capable of sending a command to Voyager 2, and it is a 70-meter dish in the hills outside an Australian city. In 2020, that dish was taken offline for 11 months for critical upgrades. For those 11 months, Voyager 2 could speak to us, and we could not answer. Both spacecraft also carry something that has nothing to do with science. Bolted to the side of the 10-sided body, in an aluminium cover, is a gold-plated copper phonograph record, 12 inches across, with a cartridge and a stylus tucked in beside it, and pictogram instructions etched onto the case explaining how to play it. The committee that assembled it had about 6 weeks. It was chaired by Carl Sagan, and its members included the astronomer Frank Drake, the writer Timothy Ferris, the artist John Lomberg, and the creative director Anne Druyan. And, on the record, they put 115 images, encoded as audio, greetings in 55 languages, about 90 minutes of music, ranging from Bach to Chuck Berry, to a Navajo night chant, to Bulgarian folk singing, and a sequence of sounds from Earth, including surf, thunder, a mother speaking to a child, and the songs of humpback whales. Druyan also had her brain activity recorded for an hour, compressed into a few seconds of audio on the disc. She has said since that on the day of the recording, she and Sagan had become engaged 2 days earlier, over the telephone, and that during the hour she thought about that. On the cover there is a diagram, drawn by Drake, showing the position of the Sun relative to 14 pulsars, each one identified by its rotation period. It is a map. It is also a clock, because pulsars slow down at known rates, so anything that found the record could work out roughly when it was launched. In one corner there is a small patch of electroplated uranium-238, which decays at a known rate, as a second and independent way of dating it. None of that is why the mission matters now. The record is a gesture. It was understood as a gesture at the time. Sagan himself observed that nothing was likely to find it, and that the point was the making of it. What matters now is that these two objects were built with an obsessive, almost pathological conservatism by engineers who assumed everything would break. There are 2 of nearly every system. When the radiation belts of Jupiter turned out to be far more intense than expected, Voyager 1 absorbed something like 1,000 times a lethal human dose during its flyby. The spacecraft survived because the designers had wrapped the critical wiring in aluminium foil and had built-in margin they could not justify to anyone on the budget committee. That conservatism is the reason a 5-year mission is in its 49th year. But the margin is finite, and it is nearly gone. The plutonium has a half-life of 87.7 years, and the thermocouples degrade as well, so the available power falls by about 4 watts every year. The generators that produced 470 watts at launch now produce a little over 200. Every instrument still running is running because someone at the Jet Propulsion Laboratory made a decision that it was worth more than something else that was turned off. In February of 2025, the cosmic ray subsystem on Voyager 1 was switched off. In March of that year, the low-energy charged particle instrument on Voyager 2 was switched off. In April of this year, the same instrument on Voyager 1 was switched off, after operating almost continuously since 1977. Voyager 1 now has two working science instruments. One measures magnetic fields, one listens to plasma waves. Those two are not a random remnant. They are the two that measure the thing the spacecraft was never designed to find in a place nobody expected it to reach. Because when these machines were built, the destination was Jupiter and Saturn. What lay beyond them was not a target. It was a diagram, a clean line drawn on a page by people who had never been there, and who had every reason to believe the line was where they said it was. That diagram had a name and a history, and one very specific weakness. Nobody had ever measured it. For most of the 20th century, the space between the planets was understood to be empty. Not almost empty. Empty. A vacuum, cold and inert, through which the planets moved without resistance, and in which nothing happened. There was one persistent piece of evidence against that, and it had been sitting in plain view for centuries. Comets have two tails. One is made of dust, and it curves, trailing behind the comet along its orbit in the way you would expect of something being left behind. The other is made of ionized gas, and it does something different. It points directly away from the sun, always, regardless of which way the comet is traveling. When a comet rounds the sun and heads back out, its ion tail runs ahead of it. In 1951, a German astronomer named Ludwig Biermann worked through what that required. Sunlight alone could not do it. Radiation pressure from photons was far too weak to push ionized gas that hard, by something like a factor of 100. Something else was coming off the sun and hitting the tail. Biermann concluded that the sun must be emitting a continuous stream of charged particles in every direction, at all times, and that this stream was what the comet tails were showing us. He called it solar corpuscular radiation. Most people did not accept it. The prevailing model, developed by the British geophysicist Sidney Chapman, held that the sun's outer atmosphere, the corona, was extremely hot, but essentially static. It extended a long way. It might even reach past the Earth's orbit. But it sat there. It did not flow. The problem with a static corona is arithmetic, and it took a young physicist at the University of Chicago to notice how bad the arithmetic was. Eugene Parker was in his early 30s in 1958. He took Chapman's own model of a hot, extended corona and followed it outward. If the corona is 1,000,000 degrees at its base and remains hot as it extends, then at large distances its pressure does not fall to zero. It settles at some finite value, and that finite value is considerably higher than the pressure of the interstellar gas outside. A gas at higher pressure than its surroundings, with nothing containing it, does not sit still, it expands. And as it expands outward through a widening volume, the flow accelerates, and past a certain distance from the sun, it becomes supersonic. Parker's conclusion was that the corona is not an atmosphere at all. It is an outflow. It is the sun continuously boiling itself off into space, at hundreds of kilometers per second, in all directions, forever. He named it the solar wind. The paper went to the Astrophysical Journal, and both referees rejected it. One of them told him, in effect, to go and read the literature before writing again. Parker appealed to the editor, who was Subramanian Chandrasekhar. Chandrasekhar had been through something comparable himself, 20 years earlier, when Arthur Eddington publicly demolished his work on the maximum mass of white dwarfs in front of the Royal Astronomical Society work that was correct, and that would eventually earn him a Nobel Prize 4 decades later. Chandrasekhar read the referee reports, could find no actual error in Parker's mathematics, overruled both referees, and published it. 4 years later, the argument ended. The Soviet probes Luna 1 and Luna 2 carried ion traps that measured a continuous stream of plasma flowing past them. Then, in 1962, Mariner 2, on its way to Venus, measured the wind directly and continuously for nearly 4 months. The speed was between about 300 and 800 kilometers per second, exactly in Parker's range. It varied. It gusted. It never stopped. The sun is losing mass at a rate of roughly 1,000,000 tons a second. That figure sounds enormous, and it is essentially irrelevant to the sun, which has enough mass that it could keep this up for far longer than it will live. What matters is not the amount, but the persistence. 1,000,000 tons a second, sustained for 4.5 billion years, blowing outward in every direction. That flow has to end somewhere. It ends where it runs into something pushing back. The space between the stars is not empty either. It contains gas, dust, magnetic fields, and cosmic rays, and all of those exert pressure. So the solar wind expands outward until its pressure has dropped, through simple geometric dilution, to the point where it equals the pressure of the interstellar material. There, it stops. It cannot go further. And the volume it has carved out of the galaxy, a cavity in the interstellar medium, filled with material from the sun and swept clear of most of the material from outside, is called the heliosphere. The heliosphere is not the solar system in the usual sense. It has nothing to do with the planets or with the sun's gravity, which extends far beyond it. It is a bubble of influence defined by pressure balance, and its outer skin is called the heliopause. Inside the heliopause, the plasma around you came from the sun. Outside it, the plasma around you came from the galaxy. That is the whole of the definition. It is a boundary between two kinds of gas. Before Voyager, the best estimates put the heliopause somewhere around 100 astronomical units from the sun. 1 astronomical unit is the distance from the Earth to the sun, about 150 million kilometers. So, 150 million kilometers, 150 million kilometers, multiplied by 100, roughly 15 billion kilometers, far past Neptune, far past the bulk of the Kuiper belt, but nowhere near the outer reaches of the sun's gravitational hold, which extends outward through the Oort cloud to something like a light year and a half. It is worth pausing on that distinction, because it is the single thing most often got wrong about where the solar system ends. There are two completely different boundaries, and they are nowhere near each other. The first is the one we have been discussing, the heliopause, defined by pressure, sitting at somewhere between 100 and 130 astronomical units. That is the boundary of the sun's plasma and magnetic influence. It is what Voyager crossed. The second is gravitational, and it is much further out. The sun's gravity does not stop at the heliopause. Gravity has no cutoff, and it holds objects far beyond the region its wind can fill. Out there, beginning perhaps 2,000 astronomical units from the sun and extending to something like 100,000, a light and a half year, roughly a quarter of the way to the nearest star, is the Oort cloud, a vast, extremely sparse population of icy bodies gravitationally bound to the sun, from which long-period comets fall inward. Nothing has ever been there. Its existence is inferred entirely from the orbits of the comets that arrive from it, which come in from all directions rather than from the plane of the planets, and with orbital periods of thousands or millions of years. Jan Oort worked this out in 1950 from a statistical analysis of comet orbits, and the picture has not fundamentally changed since. So there are two answers to where the solar system ends, differing by a factor of about 1,000. Voyager 1, at 167 astronomical units, is outside the sun's plasma bubble and is nowhere near out of the sun's gravitational domain. It will take roughly 300 years to reach the inner edge of the Oort cloud, and perhaps 30,000 years to pass through it entirely, and it will not detect anything on the way, because the objects out there are separated by tens of millions of kilometers and nothing will come close enough to see. Tonight is about the first boundary, but it is worth knowing that the spacecraft that supposedly left the solar system 14 years ago is, by the other definition, still deep inside it, and will be for the whole of recorded human history to come. The predicted structure of the first boundary had 3 parts, in order. First, at some distance, the supersonic solar wind would encounter enough resistance to drop abruptly to subsonic speed. That is a shock, the same kind of transition that produces a sonic boom, or the standing ring you see in a kitchen sink, where the falling water spreads out and suddenly thickens. This one was called the termination shock. Second, beyond the shock, a region of slowed, compressed, heated solar wind, turning aside and flowing off into a long tail behind the moving solar system. That region was called the heliosheath. Third, at the outer edge of the heliosheath, the heliopause itself, the surface where solar material stops and interstellar material begins. And beyond that, according to everything anyone knew in 1977, was as close to nothing as the galaxy gets. The local interstellar medium was thought to be extremely thin, on the order of a fraction of an atom per cubic centimeter, and undisturbed, cold, or at least quiet, featureless. The word people used, and it was not a careless word, was void. The picture was not a guess. It was built out of good physics and good observations by careful people. Parker's equations were correct. The pressure balance argument is correct. The three-layer structure is, in broad outline, correct. Nothing about the model was sloppy, but every number in it describing the outside came from remote observation. You cannot put a probe in interstellar space and read a dial. So instead you look at a distant star, take its spectrum, and see which wavelengths have been absorbed by the gas lying between that star and you. From the depth of the absorption lines, you can work back to how much material the light passed through. That gives you a total, smeared along the entire line of sight, hundreds or thousands of light years of gas, averaged into a single number. An average along a line of sight tells you nothing about structure. If the light passed through one very dense cloud and then a great deal of nothing, you get the same answer as if it passed through a uniform medium of moderate density. The technique cannot distinguish between those, and for a long time there was no strong reason to think it needed to. There is a second problem, and it is worse. The solar system does not sit in average galactic material. It sits inside a hole. Astronomers had begun to notice, by the 1970s and 80s, that the gas immediately around the Sun was unusually sparse and unusually hot, and that this condition persisted out to a considerable distance in every direction. The name that attached to it was the local bubble. The current picture, which comes largely from mapping stellar distances and dust extinction with the space telescope Gaia, is that it is a cavity roughly 1,000 light-years across, blown out of the interstellar medium by a series of supernovae, perhaps 15 of them over the last 14 million years. Older estimates put it closer to 300 light-years across. The number has moved as the mapping has improved, and it may move again. So the material the Voyagers were heading toward was not typical galactic material. It was the inside wall of a supernova cavity, and whatever was in it was there because of specific explosions with specific histories, not because of any general property of the galaxy. Nobody knew what that meant in detail, because nobody had been. And so the model went into the textbooks, and into the classroom diagrams, and into the mission planning documents, with its clean line, and its labelled layers and its empty outside. It was reasonable. It was elegant. It fit everything that could be measured from here. It was also, in a very specific sense, a hypothesis that had never once been tested against a direct measurement, and it would remain untested for another 3.5 decades until a spacecraft that was built for an entirely different purpose, by people who were not thinking about the heliopause at all, happened to still be working when it got there. That spacecraft only existed because of an accident of celestial mechanics, and a graduate student who was given a piece of routine homework and did not treat it as routine. In 1965, a doctoral student named Gary Flandreau was working a summer job in the mission analysis section at the Jet Propulsion Laboratory. He was given a task that nobody senior wanted: work out how you might get a spacecraft to the outer planets. Not a specific mission, just the general problem. The general problem was, on its face, hopeless. Jupiter is 5 times further from the Sun than Earth. Neptune is 30 times further. With the rockets available then, and with a direct trajectory, a probe sent to Neptune would take something like 30 or 40 years to arrive, and it would arrive with almost no energy left and no way to slow down. There was no realistic way to do it. Flandreau did what you do with a problem like that. He got out the ephemeris tables and started plotting where each of the outer planets would be, decade by decade, into the future. The technique he was interested in already existed on paper. If you fly a spacecraft past a planet and you set up the geometry correctly, the spacecraft steals a small quantity of the planet's orbital momentum and leaves faster than it arrived. The planet loses an unmeasurably tiny amount of speed in exchange. It is not free energy, but it is very nearly free from the spacecraft's point of view, and it is the only way to reach the outer solar system on a human timescale. Michael Minovich, working at the same laboratory a few years earlier, had done much of the foundational mathematics. What Flandreau found in the tables was that Jupiter, Saturn, Uranus, and Neptune were all going to be strung out along the same broad arc of sky in the late 1970s. A spacecraft launched in a window around 1977 could swing past Jupiter, be flung onto Saturn, be flung on from there to Uranus, and from there to Neptune. 4 planets, 1 launch. The travel time to Neptune dropped from decades to about 12 years. The alignment recurs roughly every 176 years. The previous one had passed during the presidency of Thomas Jefferson. If this one were missed, the next would come in the 22nd century. The response inside NASA was a proposal called the Grand Tour. 4 large, ambitious spacecraft, 2 of them going to Jupiter, Saturn, and Pluto, and 2 going to Jupiter, Uranus, and Neptune. It was designed around a new generation of self-repairing computer hardware. It was expensive. In 1972, with the Apollo program winding down and budgets contracting, it was cancelled. What survived was a much smaller program, approved under the name Mariner Jupiter-Saturn 1977. 2 spacecraft, Jupiter and Saturn only. A 5-year mission. The name was changed to Voyager a few months before launch. There is a detail here that says a great deal about how large projects actually get done. The engineers building the 2 probes knew perfectly well that the trajectory that took Voyager 2 past Saturn could, with the right aim point, continue to Uranus and then to Neptune. They were not funded for that. They were not permitted to design for it. So they designed the spacecraft to survive well beyond its 5-year requirement anyway, and they kept the option open in the trajectory, and they did not make a great deal of noise about it. When the Saturn encounter succeeded and the spacecraft was healthy, the extension to Uranus was approved almost as a formality, because the hardware was already there and already capable. Voyager 2 launched first on the 20th of August 1977 on a Titan IIIe Centaur from Cape Canaveral. Voyager 1 launched 16 days later on the 5th of September on a faster trajectory that would overtake its twin before Jupiter. The numbering, which confuses people, refers to arrival order, not launch order. The launches themselves were not smooth. Voyager 2's Centaur upper stage burned longer than planned to compensate for a problem, and ended with so little propellant remaining that the margin was measured in seconds. Then, once in space, Voyager 2's onboard fault protection misinterpreted the launch environment, decided the spacecraft was in trouble, and began executing recovery sequences on its own, including deploying the science boom early and cycling systems in a way that alarmed everyone watching the telemetry. Then, in April of 1978, Voyager 2's primary radio receiver failed. The spacecraft switched to its backup. The backup had a failed capacitor in its tracking loop, which meant it could no longer lock onto a range of frequencies and follow a signal as it drifted. It could only hear a very narrow band, and that band shifted with the temperature of the spacecraft. That failure has never been fixed and never will be. For 48 years, every command sent to Voyager 2 has had to be transmitted at a precisely pre-computed frequency, accounting for the Doppler shift from the Earth's rotation, the Earth's motion around the Sun, the spacecraft's motion, and the current thermal state of the receiver. If the calculation is wrong by a small amount, the spacecraft does not hear it. And append, every command for half a century has been threaded through a broken part. The planetary encounters, when they came, were extraordinary in the specific sense that they replaced guesses with images. Jupiter, in 1979, came to Saturn in 1980 and 1981, Uranus in 1986, Neptune. In 1989, Voyager 2 remains the only spacecraft ever to have visited the 2 outermost planets, and there is currently no approved mission to return to either. One moment from Jupiter is worth stopping on because of how it happened. 3 days after Voyager 1's closest approach, a navigation engineer named Linda Morabito was doing routine work. Her job was optical navigation, taking long exposure images of a moon against the background stars in order to fix the spacecraft's position precisely. To bring out faint stars, she had heavily overexposed a frame of Io. She was looking for stars. At the edge of Io's disk, there was a crescent-shaped smudge, about 300 kilometers tall, hanging off the limb of the moon into black space. Her first assumption was an imaging artifact, then that it was another moon behind Io. She checked the ephemeris. There was no moon there. She worked through the possibilities methodically and eliminated them one at a time, and arrived at the only remaining answer, which was that she was looking at an eruption, a plume of material thrown 280 kilometers above the surface of a moon that everybody had expected to be a dead ball of rock. What made it stranger is that the answer had already been published. 3 days before the flyby, a paper had appeared in Science by Stan Peele, Patrick Casson, and Ray Reynolds, predicting on purely theoretical grounds that tidal heating from Jupiter would keep Io's interior molten and that its surface should show widespread volcanism. The paper ended by noting that Voyager might see it. It saw it 3 days later. Io turned out to be the most volcanically active body in the solar system, and it is still resurfacing itself today. It is the pattern the whole mission follows. The instruments were built for one purpose. The discovery came from somebody looking carefully at data collected for a different reason, noticing that something in the frame did not belong, and refusing to dismiss it. Not everything worked. During the Saturn encounter in 1981, Voyager 2's scan platformed the movable mount that aims the cameras and spectrometers jammed in azimuth. It had been running at high slew rates for hours, and a lubricant had migrated out of a bearing. The platform seized shortly after closest approach, and a substantial fraction of the planned Saturn observations were lost. The fix, which had to work at Uranus 5 years later, was partly operational and partly physical. Engineers worked out that the bearing recovered if it was left alone, and that the damage came from sustained fast slewing. So they rewrote the observation sequences to move the platform slowly and rest it frequently. And for the observations that still needed motion the platform could not provide, they rolled the entire spacecraft instead, tracking targets with the whole vehicle while it flew past Uranus at over 18 kilometers per second, in light levels 400 times fainter than at Earth. The images from Uranus and Neptune required exposures long enough that the spacecraft had to be turning, precisely, throughout the exposure, to hold the target still on the detector. They also had to reprogram both spacecraft in flight to compress data more aggressively, because the original data rates assumed distances from Saturn, not Neptune. The flight data subsystem was rewritten, and the new code was uploaded across billions of kilometers to a computer with kilobytes of memory, and it worked. And in 1980, in the middle of all of this, something failed on Voyager 1 that would matter more than anyone realized at the time. Its plasma science instrument stopped returning usable data. This was the instrument built to measure the density, temperature, and bulk velocity of the charged particles the spacecraft was flying through 4 Faraday cups, 3 aimed roughly sunward and 1 aimed sideways, counting ions and electrons directly. It had done its job at Jupiter and Saturn. Then a component in its power supply failed, and it went quiet, and there was nothing anyone could do about it. It was formally powered off decades later to save the watts. Voyager 1 would spend the rest of its life without the ability to directly measure the plasma it was moving through. The planetary mission ended on the 25th of August, 1989, at Neptune. The following year, on Sagan's long campaign, Voyager 1 turned its cameras around one last time and photographed the planets from 4 billion miles out, producing the frame in which the Earth occupies less than a pixel. Then the cameras were switched off permanently to save power, and because there would be nothing more to photograph. The public moved on, the spacecraft did not. What was left was 2 working machines with a handful of live instruments, moving outward at 17 and 15 kilometers per second respectively, into a region that had never been sampled, with a mission objective that had been quietly rewritten. They were now looking for the edge, and the first thing they had to survive was the next 25 years of nothing happening at all, on a power budget that fell every single year. There is a particular kind of work that consists almost entirely of deciding what to give up next, and doing it slowly enough that nobody notices, for 35 years. The arithmetic of the Voyager power budget is not complicated. 4 watts a year, every year, without exception or reprieve. The plutonium decays whether or not anyone is watching. The thermocouples degrade whether or not the mission is funded. At launch there were 470 watts. By the mid-1990s there were around 330. By 2020, around 250. Today, a little over 200. Against that, the spacecraft has fixed costs it cannot reduce. The radio has to transmit, or there is no mission. The computers have to run, and a great deal of the budget, more than most people would guess, goes to heaters, because the fuel lines carrying hydrazine to the attitude thrusters will freeze solid at around 2 degrees Celsius. And if they freeze, the spacecraft loses the ability to point its antenna at Earth. And if it cannot point its antenna at Earth, then everything else is irrelevant. So the decisions have all been variations on the same question. What can we stop keeping warm? The instrument heaters went first, and this produced one of the small, persistent oddities of the mission. Instruments designed to operate down to minus 35 degrees Celsius were left unheated and fell to minus 60, minus 70, minus 79. They kept working. The cosmic ray subsystem ran for years at temperatures well below anything it had been qualified for. Nobody had tested the hardware that cold because nobody had imagined a reason to. It turned out that a certain class of 1970s electronics, built with generous margins and no miniaturization, simply does not care. The ultraviolet spectrometer on Voyager 1 was left on far longer than planned, because it was the only instrument of its kind anywhere in the outer solar system. It was finally switched off in 2016. The plasma science instrument on Voyager 2, the one that still worked, was switched off in October of 2024, after 47 years. Presiding over most of this was Ed Stone. He became project scientist for Voyager in 1972, 5 years before launch, and he held that position for 50 years, stepping down in 2022 at the age of 86. 50 years is not a career on a project, it is the project. Stone's colleagues describe a particular discipline in him. He refused, consistently, to describe results in language stronger than the data supported, and he refused to let the mission be discussed as a piece of nostalgia. His position was that Voyager was an operating observatory in a region nobody else could reach, and that its data was current data, not historical data. He also held a weekly science meeting for decades and read essentially everything. He died in June of 2024, aged 88. The spacecraft outlasted him and are still returning data. The project manager since 2010 has been Suzanne Dodd, who first worked on Voyager in 1984 as a young engineer building command sequences for the Uranus encounter, left for other missions, and came back 26 years later to run it. One of the practical problems she inherited is that the people who designed these spacecraft are retired or dead, and the documentation is paper, and some of it was written in a hurry in 1975 and stored in boxes. Current engineers have spent significant time reading 50-year-old memoranda in order to understand why a particular circuit does what it does. 3 episodes from the last few years show what operating this mission now actually involves. The first began in May of 2022. Voyager 1's attitude control system, the computer that keeps the antenna pointed at Earth, started sending back telemetry about its own status that was plainly wrong, randomly formatted, impossible values, and yet the system itself was clearly working because the antenna stayed pointed and the science data kept arriving correctly. The spacecraft was functioning perfectly while filing incoherent reports about itself. It took months. What the team eventually determined was that the attitude control system had, at some point, begun routing its telemetry through an onboard computer that had stopped working years earlier, which was corrupting the data on the way past. They did not repair anything. They commanded the system to route its telemetry somewhere else. The reports became coherent again. Why? It started using the dead computer in the first place was never established, and the working theory involves a faulty command generated by another onboard system, possibly years earlier. The second episode was worse, and it was self-inflicted. In July of 2023, a routine sequence of commands sent to Voyager 2 contained an error that tilted the spacecraft's antenna about 2 degrees away from Earth. 2 degrees. At 19 billion kilometers is enough. Contact was lost completely. No data came down. No commands could be received. There was a fallback. The spacecraft is programmed to reset its own orientation several times a year, and the next reset was scheduled for the 15th of October, so the worst case was known. Silence until October then, probably recovery. The team did not want to wait 11 weeks. In early August, the Canberra dish, the only antenna on Earth that can transmit to Voyager 2, sent the command sequence at the highest power available, aimed at where the spacecraft should be, on the chance that enough signal would spill into the misaligned antenna to be understood. The round trip was 37 hours. They sent it, and then waited a day and a half to find out whether anything had happened. Something had. The spacecraft heard it, reoriented, and locked back onto Earth. The third episode is the one that came closest to ending the mission. On the 14th of November, 2023, Voyager 1 stopped making sense. The carrier signal was still there. The spacecraft was still responding to commands. But the data stream had become a single repeating pattern of ones and zeros, endlessly, with no science and no readable telemetry inside it. The flight data subsystem, the computer that packages everything for transmission, had failed in some way, and because its own status reports came through the same broken channel, it could not be asked what was wrong. The team spent 5 months on it. Every experiment took at least 45 hours, because a command takes about 22.5 hours to arrive, and any response takes the same time to return. There is no debugging cycle faster than 2 days. In March of 2024, they sent what they called a poke, a command telling the flight data subsystem to run a different sequence of its own software, in the hope that something would react differently. 2 days later, a signal came back that was not the endless repeating pattern. Buried in it was a readable dump of the computer's memory. Comparing that dump against how the memory should have looked, they located the fault. A single chip, holding about 3% of the system's memory, including a section of the code that assembles data for transmission. Something had destroyed it, possibly a cosmic ray strike, possibly 46 years of accumulated degradation. There was no way to repair it, and no spare. So they took the code that had been living on the dead chip, cut it into pieces small enough to fit in the gaps of memory, still working elsewhere, distributed those pieces around the system, and rewrote every reference in the rest of the software to point at the new locations. They did this on a machine built before the personal computer, with a 2-day delay on every test. On the 20th of April, 2024, Voyager 1 sent back readable engineering telemetry for the first time in 5 months. By June, the science data was flowing again. There is also a slow mechanical problem that has nothing to do with computers. The thrusters that keep the antenna aimed fire in tiny pulses dozens of times a day, and have done so for nearly half a century. The fuel lines are gradually silting up with silicon dioxide, shed from a rubber diaphragm inside the propellant tank. The tubes that inject fuel into the thrusters started at about 1/4 of a millimeter wide. In some of them, the opening has narrowed to a small fraction of that. When a thruster branch clogs enough to be unreliable, the team switches to another set, and in 2025 they successfully revived a backup roll thruster set that had been considered dead since 2004 in order to have something left to switch to. Which brings this to the present. Right now, in the middle of 2026, the team is preparing an intervention they refer to as the Big Bang, turning off a whole group of powered devices at once and substituting lower power alternatives in order to keep the spacecraft warm enough to keep doing science. They are trying it on Voyager 2 first, because it has slightly more power in hand and is a few billion kilometers closer, which makes it the safer test. If that works, Voyager 1 follows. The goal is to still have at least one instrument running on each spacecraft into the 2030s. I want to be careful not to make this sound heroic in the way that press releases make things sound heroic. Most of this work is not dramatic. It is people reading old documents, running the same test again, arguing about margins, and waiting 2 days for an answer. The drama, such as it is, comes entirely from the fact that the object they are maintaining cannot be reached, cannot be inspected, and cannot be replaced, and that every mistake is permanent. But the reason it matters is straightforward, and it is not sentimental. Voyager 1 and Voyager 2 are the only 2 objects human beings have ever placed outside the heliosphere. There is no third. There is no successor funded, built, or launched. When these 2 go quiet, and they will, within the next decade, direct measurement of the interstellar medium stops and does not resume for a very long time. Everything we know from inside that region, we know because 2 machines from the 1970s were kept running by people who kept finding one more thing to switch off. And the first thing those machines found, when they finally got out past the planets and into the region the diagrams had labelled so confidently, was that the diagram's first boundary was in the wrong place. A shock in this context is not an impact. Nothing collides. A shock is what happens when a flow moving faster than the speed at which information can travel through it runs into something that requires it to slow down. In ordinary air, information travels as sound, and the relevant limit is the speed of sound. In a plasma threaded with a magnetic field, there are several such speeds, and the relevant one is faster, but the principle is identical. If the flow is subsonic, the material downstream can send a signal upstream, a pressure wave, telling the oncoming flow that there is an obstacle, and the flow adjusts smoothly and goes around. If the flow is supersonic, no signal can get upstream. The flow arrives without warning, hits the region where it must slow, and has no choice but to do so almost instantaneously, in a layer that may be thinner than the distance between the particles making it up. You have watched this happen. Turn a tap on hard into a flat sink. The water spreads out from the point of impact in a thin, fast, glassy sheet, and then at some radius, it abruptly thickens into a slower, turbulent ring. That ring is a standing hydraulic shock. The sheet inside is moving faster than waves can travel in it. The water outside is not. The boundary is sharp because it has to be. The termination shock is the same object, made of solar wind, roughly 15 billion kilometers across. The kinetic energy the flow had is not destroyed at the transition. It gets converted, mostly into heat and into magnetic field compression. So the theory predicted a very specific signature: an abrupt drop in bulk flow speed, an abrupt jump in density, an abrupt jump in temperature, an abrupt jump in the strength of the magnetic field, and a burst of particles accelerated by the shock itself to high energies. That last one was thought to be important for a reason beyond the shock. There is a class of cosmic ray called anomalous cosmic rays, which had been detected near Earth for decades, and which are chemically peculiar. They are rich in elements like helium, oxygen, neon and nitrogen, and poor in the things that dominate ordinary galactic cosmic rays. The accepted explanation was that they begin as neutral atoms from interstellar space, which drift into the heliosphere unimpeded because they carry no charge, get ionized by sunlight somewhere inside, and are then picked up by the solar wind and carried outward. At the termination shock, the theory said, these pickup ions get accelerated to high energy, and some of them come back inward. Find the termination shock, and you should find the factory. Voyager 1 reached it on the 16th of December, 2004, at 94 astronomical units from the Sun, about 14 billion kilometers. The distance was lower than most predictions, which had clustered around 100 astronomical units or beyond. That immediately said something. The heliosphere was smaller than the models had it, which meant the pressure from outside was higher than the models had assumed. But Voyager 1's plasma instrument had been dead since 1980. It could not measure the flow speed, so the crossing had to be inferred from the magnetometer, which saw the field strength jump, and from the particle detectors, which saw the count rates change character. The evidence was good. It was not direct. It also arrived after a long argument. Between 2002 and 2003, Voyager 1's particle detectors had already registered a period of strange behavior that several researchers interpreted as an early shock crossing. Others disagreed. There were competing papers in the same issue of Nature in 2003, reaching opposite conclusions from overlapping data. What eventually resolved it is that the shock does not stay still. It moves in and out by several astronomical units as the pressure of the solar wind rises and falls, and a spacecraft creeping outward at 3.5 astronomical units per year can be overtaken by it repeatedly. Voyager 2 settled the matter, because Voyager 2 still had a working plasma instrument. It crossed on the 30th of August, 2007, at about 84 astronomical units, and then crossed again and again. Over the course of a few days, the shock washed back and forth across the spacecraft at least 5 times. The instruments recorded each pass. It was not a wall that the probe went through once. It was a surface in motion, and the spacecraft was near enough to it that the surface kept overtaking it. 2 things about that crossing were not what anyone expected. The first was the distance, 84 astronomical units against Voyager 1's 94. The 2 spacecraft left the solar system in very different directions. Voyager 1 heading north out of the plane of the planets, Voyager 2 heading south, and the boundary was about 10 astronomical units closer on Voyager 2's side. That is 1.5 billion kilometers of difference. The heliosphere is not a sphere. It is pushed in on one side. The obvious candidate for what is pushing it is the interstellar magnetic field, which does not lie neatly along any axis we would have chosen and which presses on the bubble unevenly. That asymmetry would become one of the persistent themes of everything that followed. The second surprise was the temperature, and it was a real one. Voyager 2 measured the solar wind, slowing from supersonic to subsonic, as predicted. It measured the density rising, as predicted. It measured the magnetic field strengthening, as predicted. And then it measured the temperature of the solar wind protons after the crossing, and found something like 180,000 degrees, when the models had predicted well over 1 million. The energy had gone somewhere. It had not gone into heating the ordinary solar wind. The explanation that emerged is that the energy was absorbed by the pickup ions, those interstellar atoms that had drifted in, been ionized, and been swept along. They make up a small fraction of the particles by number, but because they were picked up moving at solar wind speed relative to the flow, they carry a disproportionate share of the energy, and at the shock, they took most of what was released. The bulk of the heating went into a minority population that the plasma instrument could not properly see. That is not a rounding error. It means the outer heliosphere is not primarily a solar wind plasma at all, in terms of where its energy and its pressure live. It is dominated by material that came from outside and was captured. The bubble is, energetically, substantially made of the thing it is supposed to be keeping out, and the anomalous cosmic rays were not there. This was the clean prediction, the one everybody expected to confirm. The intensity of anomalous cosmic rays did not peak at the shock. It kept rising as the spacecraft moved further beyond it, which means the source region was somewhere else further out, or along the flanks of the shock where the geometry is different, or in the heliosheath itself. 2 decades later, the question is not fully settled. The most favoured explanations involve acceleration along the sides of the shock rather than at the point where the spacecraft crossed, where the magnetic field geometry is much more favourable for kicking a particle repeatedly across the boundary. So, the first boundary the mission ever reached delivered a mixed verdict. The structure existed, and it was roughly where and what the theory said. Its location was wrong by 10%, its shape was wrong, its heating was wrong by a factor of 5, and the one thing it had been confidently expected to produce, it did not produce. Consider what it would be like to be there. You are 94 astronomical units from the Sun. The Sun is still the brightest object in your sky, by an enormous margin. It would be about as bright as a full moon is on Earth, which is to say you could not read by it, but you would never mistake it for a star. Everything else is unchanged. The constellations look exactly as they do from your window. You have travelled 14 billion kilometres and the sky has not moved. There is no wall in front of you. There is nothing to see at all. The material you are moving through is so thin that if you took a cubic metre of it and collected every particle, you would have a few thousand atoms. A cubic metre of the best vacuum ever produced in a laboratory on Earth contains vastly more than that. And yet there is a surface here, and you cross it, and on the far side, the wind that has been at your back since you left is no longer at your back. It has slowed, and turned, and thickened, and begun to flow sideways. Nothing about this is visible. It is entirely a property of a gas so thin it is barely a gas, and you would only know it had happened because a magnetometer on a boom 13 meters behind you registered that the field strength had doubled. That is the character of the whole region. Everything that happens out here happens to a medium you could not detect with any human sense, and the structures are the size of solar systems. Beyond the shock lay the heliosheath, the layer of slowed, hot, compressed solar material that has to be somewhere, because the wind is still arriving from behind at 1 million tons a second, and it has to go somewhere. Theory said it should be a relatively orderly place, turbulent certainly, but a coherent flow, bending around and heading off into a long tail behind the moving solar system, with a magnetic field that spirals as it always has, only more tightly. The models put its thickness at somewhere between 5 and 30 astronomical units. Voyager 1 entered it in 2004 and did not leave it until 2012. 8 years, at 3.5 astronomical units a year, almost 30 astronomical units of it, at the top end of every prediction. Voyager 2, entering closer in, took 11 years to get through, And what the two spacecraft found inside that layer had no counterpart in any model, and it changed what the outer heliosphere is understood to be made of. It was not a sheath, it was a foam. To understand what the heliosheath turned out to be, you need one piece of background about the Sun's magnetic field, and it is not complicated. The Sun's magnetic axis is tilted relative to its rotation axis by something between 10 and 30 degrees depending on where it is in its cycle. The magnetic field is dragged outward by the solar wind, so as the Sun rotates roughly once a month, the tilted magnetic equator sweeps up and down past any fixed point in the outer solar system. The result is a surface, separating the region where the field points broadly outward from the region where it points broadly inward, and because the Sun rotates while the wind flows radially outward, that surface is drawn into a spiral and then folded into waves. It is called the heliospheric current sheet, and the standard description of it, a ballerina's skirt, is genuinely the best one available. So I will use it once and then leave it alone. Any spacecraft sitting out in the solar wind therefore sees the magnetic field reverse direction every couple of weeks, as the folds of that sheet wash over it. This is ordinary. It has been measured since the 1960s. The regions between the reversals are called sectors. Now compress all of that. At the termination shock, the wind slows by a factor of several, and the field strengthens correspondingly. The folds of the current sheet, which out in the wind are tens of millions of kilometers apart, get squeezed together into a much thinner stack. And when oppositely directed magnetic fields are pressed close enough together, they do something specific. They reconnect. The field lines break and rejoin in a new configuration, releasing energy and rearranging the topology. In 2011, Merav Ofer of Boston University and Jim Drake of the University of Maryland published a model of what happens when the folded current sheet arrives at the heliosheath and starts reconnecting. What comes out is not a smooth compressed spiral. The nested folds pinch off the same instability that makes a stretched sausage-shaped magnetic structure break into segments, and each pinched-off piece closes on itself into a self-contained magnetic loop. The heliosheath, in this picture, is not a continuous magnetic layer at all. It is a mass of separate magnetic bubbles, each of them roughly 1 astronomical unit across, 150 million kilometers per bubble. The distance from here to the Sun, per bubble, packed together across a region tens of astronomical units thick. The Voyager data supported it. Both spacecraft, moving through the heliosheath, recorded exactly the pattern you would get from passing through a froth of closed magnetic cells, the field holding a steady orientation for a stretch, then snapping abruptly to a new one, then holding again, not a gradual rotation. Discrete transitions, with the particle populations changing across each one, as though the spacecraft were moving between sealed rooms. Voyager 1 crossed dozens of them. Voyager 2, on its own path, saw the structure too, but differently fewer of them, weaker, less organized, which suggests that the bubble field is not uniform across the whole heliosheath, but depends on latitude, or on what the Sun happened to be doing when that particular parcel of material left it. The consequence is not aesthetic, it changes what the heliosphere does. The reason a magnetic bubble matters to a charged particle is that a charged particle cannot cross a magnetic field line freely. It spirals around field lines, traveling easily along them and with great difficulty across them. A galactic cosmic ray trying to work its way inward through a smooth, ordered magnetic field has a reasonably predictable job. It scatters, loses energy, and either gets through or does not. In a way you can calculate, a galactic cosmic ray trying to work its way inward through a mass of closed magnetic loops has a much stranger job. It can get trapped inside a bubble and circulate there. It can be reflected, or it can find a gap between bubbles, a channel where the field connects through and travel down it directly, arriving with far less energy loss than it should have suffered. So the same structure makes the barrier stronger in some places and weaker in others, and which of those you get depends on details of a magnetic topology that nobody can observe directly, and that changes with the solar cycle. The tidy picture, in which the heliosphere reduces the cosmic ray flux by a calculable factor, does not survive contact with the froth. There was another finding from the heliosheath that arrived quietly and was, I think, harder to absorb than the bubbles. In 2010, Voyager 1's low-energy charged particle instrument reported that the outward speed of the solar wind had dropped to zero. The instrument could not measure velocity directly, but it could measure it indirectly by watching how the intensity of particles varied depending on the direction the detector faced. If the medium is streaming past you, particles arrive preferentially from ahead. Voyager 1's team had been tracking that asymmetry for years and watching the outward flow slow down at a steady rate of about 20 kilometers per second per year, as expected in a decelerating heliosheath. In the middle of 2010, it reached zero and stayed there. The spacecraft rolled itself over repeatedly to check, using different detector orientations over a period of months. The result held. The radial outflow had stopped. The wind was still arriving, from behind, continuously, at 1,000,000 tons a second. It was not going outward anymore. It had turned entirely sideways, flowing off toward the flanks and the tail. Voyager 1 had entered what the team began calling the stagnation region, a zone perhaps 9 astronomical units thick, immediately inside the heliopause, where the material from the Sun has stopped moving away from the Sun and is simply being pushed aside. Sit with the geometry of that for a moment. Everything the Sun has emitted for 4.5 billion years in the direction Voyager 1 was travelling arrives at that layer and stops going forward. It piles up, it turns, it leaves sideways. The layer is thick enough that a spacecraft moving at 17 kilometers per second spent more than 2 years crossing it. Inside the stagnation region, the magnetic field strength roughly doubled while the field direction stayed almost constant, and the intensity of galactic cosmic rays coming from outside began climbing steeply, while the intensity of particles from inside the heliosphere began falling. The barrier was thinning. Then, in the middle of 2012, the particle count started doing something abrupt. Over a period of days, the population of low-energy particles originating inside the heliosphere collapsed, dropping by a factor of 1,000 over about a month, with the sharpest changes taking less than a day. At the same time, galactic cosmic rays jumped upward by roughly 9% and stayed there. Particles from inside were escaping outward along the magnetic field far more easily than before, and particles from outside were arriving far more easily, but the magnetic field direction did not change. The team gave this region a name, the Magnetic Highway, and the name captures the puzzle. It appeared to be a zone where the Sun's magnetic field had connected to the interstellar magnetic field, allowing particles to run along the joined field lines in both directions, while the field itself still pointed the way solar field points. Something was open, and something else was closed. For anyone waiting to declare that the spacecraft had left the solar system, this was maddening. 2 of the 3 expected signatures had arrived, solar particles gone, galactic particles up. The 3rd, the change in field direction, had not. And the 4th, the density measurement that would have settled it in an afternoon, could not be made at all, because the instrument that would have made it had failed 32 years earlier. There were papers in 2013, with titles proposing that Voyager 1 had left the heliosphere, and papers proposing that it had not, and papers proposing that it had entered a region nobody had modelled, and one proposal that the heliopause had briefly moved inward past the spacecraft and then moved back out again. The argument was not a failure of the field, it was the correct behaviour of a field confronted with an ambiguous measurement it could not repeat. There is exactly one spacecraft in that region, it is not coming back, and there is no control. What broke the deadlock was not a new instrument or a better theory. It was the Sun doing something violent, at the right moment, in the right direction, entirely by chance. The instrument that eventually answered the question was built at the University of Iowa, and the man who ran it had been building instruments like it since he was an undergraduate. Don Gurnett grew up on a farm in Iowa and joined the university's physics department in the late 1950s, in time to work on Explorer 1, the first American satellite, the one that found the Van Allen radiation belts. He spent his career on plasma waves, and he built or co-built the wave instruments on Voyager, on Galileo, on Cassini, on Juno, on the Van Allen probes. He was the principal investigator on the Voyager plasma wave subsystem from before launch until his death in 2022, at the age of 82. The instrument itself is almost absurdly simple in concept. 2 long antennas, 10 meters each, arranged in a V. They do not detect particles. They detect electric fields oscillating voltages induced between the 2 arms by waves in the surrounding plasma. The electronics behind them split the signal into frequency channels and report how much power is in each. The physics that makes this useful is one equation, and it is one of the cleanest relationships in plasma physics. Any plasma has a natural ringing frequency. If you displace the electrons in a plasma from the ions, the electrostatic attraction pulls them back. They overshoot and they oscillate. The frequency at which they oscillate depends on nothing except the electron density, not the temperature, not the magnetic field, not the composition. Just how many electrons there are per unit volume. So if you can hear the plasma ring, you can weigh it. The frequency tells you the density directly. The difficulty is that plasma does not ring on its own, or at least it was not expected to. Something has to strike it. In practice, that meant waiting for a shockwave from a solar eruption to arrive and jostle the medium hard enough to set it oscillating. Those arrive rarely, and out beyond the heliopause they arrive after a delay of a year or more, degraded almost to nothing. Gurnett had been waiting for one for years. On the 9th of April, 2013, it came. The plasma wave instrument on Voyager 1 registered a clear oscillation at about 2.6 kHz, sustained over days. Gurnett has described the moment, and the description is unadorned. He was looking at the frequency spectrum, and the line was simply there, at a frequency that corresponded to a density about 40 times higher than anything measured inside the heliosphere, roughly 0.08 electrons per cubic centimeter. Inside, in the heliosheath, the density had been around 0.002. Then he went back through the archived data and found something he had previously dismissed. Between late October and late November of 2012, there had been a fainter, lower oscillation at about 2.2 kHz, weaker, briefer, easy to overlook. It corresponded to a slightly lower density than the 2013 event. 2 measurements, 2 densities, at 2 known positions along the spacecraft's track. That gives a gradient. Extrapolate the gradient backwards to the density you would expect at the boundary itself, and you get a position, and from the position you get a date. The 25th of August, 2012, the same day that the low-energy particles from inside the heliosphere had collapsed and the galactic cosmic rays had jumped. The particle instruments and the wave instrument, using completely independent physics, pointed at the same afternoon, 8 months in the past. The announcement was published in Science on the 12th of September, 2013. Voyager 1 had become the first object made by human beings to enter interstellar space, and it had done so more than a year before anyone was able to say so. The crossing was not an event anyone experienced. There was no signal at the time, no alarm, no moment in a control room. The spacecraft passed out of the Sun's domain in August of 2012, and everyone involved found out about it in the spring of the following year by reading a graph. Not everyone agreed even then. Tom Cremigis at the Johns Hopkins Applied Physics Laboratory had led the low-energy charged particle instrument since before launch and would keep leading it for another decade. His position was consistent, and it was not obstinate. The definition of the heliopause is where the Sun's magnetic field gives way to the galaxies, and the magnetic field had not turned. It had strengthened, it had held direction, but the direction it held was, within uncertainties, the direction the solar field had always pointed. If the field has not changed, he argued, you are still on solar field lines, and you are still inside. The counter-argument was that density is unambiguous, that a factor of 40 is not a subtlety, and that no plausible structure inside the heliosphere contains material that dense. Both sides were reasoning correctly from real measurements. The measurements disagreed. This went on, in print and in meetings, for years. The resolution, as far as it goes, is that the interstellar magnetic field near the heliosphere is not oriented arbitrarily. It is draped over the bubble and dragged and combed into partial alignment with the solar field on the side where Voyager 1 went out. 2 fields that would otherwise point in unrelated directions end up nearly parallel at the point of contact, because one of them has been bent by the other. The magnetometer was not malfunctioning, and Cremigis was not wrong about what it showed. The field really was pointing the same way. It was pointing the same way for a reason nobody had modelled, which meant the question could not be closed by one spacecraft. It needed the other one, and the other one still had a working plasma instrument. Voyager 2 crossed the heliopause on the 5th of November, 2018, at 119 astronomical units from the Sun. The plasma science instrument 4 Faraday cups on the side of the spacecraft, built at the Massachusetts Institute of Technology, operating continuously since 1977, measured the solar wind flow drop, essentially to zero over the course of a single day, and measured the electron density on the far side directly, not inferred from an oscillation, counted. The density outside was a few hundredths of an electron per cubic centimetre and rising. The two spacecraft do not report identical numbers, because they are 11 billion kilometres apart in a medium that is not uniform, but they agree on the essential thing. The density outside the heliopause is 1 to 2 orders of magnitude higher than the density inside it, and the transition is sharp. Voyager 2's crossing distance also mattered, 119 astronomical units, against Voyager 1's 121.6. Closer in, on the southern side, consistent with the asymmetry the termination shock crossings had already shown, and Voyager 2's magnetometer saw the field rotate gradually, over a broader zone than Voyager 1 had shown. But it rotated, and it rotated into an orientation consistent with what Voyager 1 had been measuring on the other side of the bubble. The interstellar field near the heliosphere is ordered. It is combed. Whatever it is doing coherently over a region billions of kilometers across. There were 5 papers published together in Nature Astronomy in November of 2019, and between them they contained 2 further details worth holding on to. The first is that just inside the heliopause, Voyager 2 passed through a thin layer where the plasma slowed down, heated up, and became denser, a compression against the inside of the boundary, like water piling against the front of a hull. It was narrow. Voyager 1's data, re-examined, showed a version of it too. The second is that the boundary leaks in both directions. Voyager 2 detected particles of solar origin outside the heliopause, measurable amounts, in a thin skin extending outward, and it detected galactic particles inside, which had begun rising well before the crossing. There is no clean surface. There is a layer, tens of millions of kilometers thick, in which material from both sides is mixed. You can, in principle, imagine standing at that boundary. There is nothing there. No transition you could see, no film, no change in the darkness. The stars are in the same places. The sun behind you is a very bright point, and nothing more. If you had a magnetometer, you would watch the field slowly turn over, a distance you would need months to travel. If you had a Faraday cup, you would find that the number of particles hitting it per second had gone up by a factor of 40, from almost nothing to slightly more than almost nothing. That is the whole of it. That is what leaving the solar system is. It is a change in the concentration of a gas so thin that the change is undetectable by any means available to a human body, occurring across a region wider than the orbit of Jupiter, and it is nevertheless the most significant boundary in the Sun's vicinity, because on one side of it, the material around you was made by our star, and on the other side, it was made by stars that died before the Sun existed. Both spacecraft are now outside. Both continue to measure. And in the years after the first crossing, the plasma wave instrument on Voyager 1 began to pick up something that had not been in anyone's prediction, because nobody had thought to predict what silence would sound like once you were finally in a position to listen to it. It turned out not to be silence. The method Gurnet used to measure the density had a built-in limitation that everyone understood, and nobody could do anything about. It required an event. A shock from the sun had to arrive, strike the interstellar plasma, and set it ringing. Between events, there was no signal, and therefore, no measurement. Over the 8 years after the crossing, that produced about 8 or 9 usable data points. A handful of readings, scattered along 30 astronomical units of the spacecraft's path, each one a snapshot taken whenever the sun happened to provide a hammer. In 2017, going through the archived plasma wave data, a Cornell doctoral student named Stella Koch-Ocker noticed something in between the events. It was extremely faint, close to the noise floor of a 50-year-old instrument at the far end of a 22-hour radio link. It was narrow, confined to a thin band of frequencies around 3 kHz, and unlike the shock-driven oscillations, it did not fade. It was there when nothing was happening. It had, once she went looking, been there almost continuously since 2017. She worked on it for 4 years, with James Cordes and Shami Chatterjee at Cornell, and with Gurnet, William Kurth and Stephen Spangler at Iowa. ruling out the alternatives one at a time. Instrumental artifact. Interference from the spacecraft's own electronics. Some slowly decaying tail of a previous shock. A processing error. None of them accounted for it. The paper was published in Nature Astronomy in May of 2021. The interstellar medium, measured from inside it for the first time, is producing a continuous, weak, narrow band emission at its own plasma frequency. It is ringing all the time. Ocker's description of it, which is the one that stuck, was that it is faint and monotone because it occupies such a narrow band of frequency. Corder's offered a comparison that I think is the useful one. The shock-driven events are lightning strikes, and this is the rain that falls between them, steady and quiet, and always there. There are two reasons this matters, and they are quite different from each other. The first is practical, and it is the reason the paper got written. A continuous signal means a continuous measurement. Before this, the density of interstellar space near the Sun was known at 8 or 9 points. Now it is known at every point along the track, because the frequency of the hum is the density, moment by moment. The spacecraft is no longer waiting to be told what it is swimming through. It is reading it off constantly. What that continuous record showed immediately is that the density is not uniform, and not smoothly varying either. Overlaid on a general upward trend, the density has climbed from roughly 0.05 to something above 0.1, 3 electrons per cubic centimetre. As Voyager 1 has moved outward, there are fluctuations, on scales of an astronomical unit or less, structure at 150 million kilometres and below. The medium is lumpy at scales that no telescope will ever resolve. The second reason is more interesting and less settled. Nobody has fully explained why the emission is narrow. Here is the difficulty. The local interstellar medium is turbulent. That is not in doubt. It is one of the best established facts about it, and Cordes has spent decades measuring that turbulence indirectly. The way you do it from Earth is by watching pulsars. A pulsar emits a sharp radio pulse. That pulse travels through hundreds or thousands of light years of ionized gas, and because the gas is clumpy, different parts of the wavefront take slightly different paths and arrive slightly out of step. The pulse smears out. The brightness twinkles. From the statistics of that twinkling, you can reconstruct the spectrum of density fluctuations along the path. Those measurements have been done for 50 years, and they agree with each other, and they say the interstellar medium is turbulent across an enormous range of scales, from thousands of astronomical units down to hundreds of kilometers, in a way that follows a fairly universal statistical law, the same broad kind of cascade that governs turbulence in a river or in the atmosphere. Turbulence is broadband. Energy enters at large scales and cascades downward through smaller and smaller eddies. If a turbulent medium is being excited, the response should be spread across many frequencies. It should be a hiss. It is a tone. The candidate explanations are all partial. One holds that the hum is a genuinely local process. Weak instabilities in the plasma, just outside the heliopause, where the interstellar material is being deflected around the bubble, generating electron beams that continuously excite oscillation at the local plasma frequency and nothing else. That would explain the narrowness. A resonance is narrow by definition, but it would also mean the hum is a property of the neighbourhood of the heliosphere, rather than of interstellar space in general, and it would not tell us much about the galaxy at large. Another holds that it is not really a single tone, but the sum of many small regions, each ringing at its own local density, and that the band appears narrow because the density does not vary much over the volume the antenna is sensitive to. That is more mundane, and probably contributes. A third possibility, and the one that would be most useful if it turned out to be right, is that the plasma is being continuously excited by the turbulence itself, and that the plasma resonance acts as a filter, taking a broad input and returning a narrow output at the frequency the medium prefers. The way a wine glass responds to a room full of noise, by humming at its own pitch. The honest position is that this is not resolved. The signal is real, it has now been observed for the better part of a decade, and there is no complete account of what drives it. It is worth being clear about what the hum is not, because the word invites a misunderstanding that is hard to shake. You could not hear it. There is nothing to hear. Sound requires a medium dense enough that a disturbance propagates by particles colliding with their neighbours. and the material out there has about 1/10 of a particle per cubic centimetre, which means the nearest neighbour of any given electron is far enough away that a collision is a rare event. Nothing carries a pressure wave in the ordinary sense. What the instrument detects is an oscillating electric field. The electrons in the plasma are moving back and forth together, and that collective motion produces a voltage between two 10-metre antennas, and the electronics report the frequency of that voltage. 3.1 kHz happens to fall within the range of frequencies human ears respond to. So if you take the recorded voltage and feed it to a loudspeaker, you get a tone. That is a translation, not a recording. It is the same operation as making a graph audible. Still, if you were out there, at the position Voyager 1 occupies, you would be surrounded by a medium in which every electron for light years in every direction is oscillating in step with its neighbours, continuously, at very close to the same frequency, and has been doing so for as long as the medium has existed. You would not detect it. Your body has no organ that responds to a fluctuating electric field of that strength. You would experience it as absolute stillness, because that is what your senses are equipped to report. The stillness is not there. It was never there. It took a 50-year-old instrument on a dying spacecraft to establish that, and the establishing of it consisted of a doctoral student noticing a faint line in a frequency plot that everyone else had been treating as background. Consider the position this leaves the field in. The local interstellar medium is the material we are physically embedded in. It is the closest example of the stuff that fills the galaxy, the stuff that stars form out of. There is one probe in it. That probe has an instrument built in the early 1970s, running on a spacecraft with a 200-watt power supply, and it is detecting a signal near the limit of its sensitivity that theory did not predict and cannot yet explain. The most obvious way to make progress would be a second measurement from somewhere else. There is no second measurement. Voyager 2's plasma wave instrument is also outside and also listening, and its data supports the picture, but the two spacecraft are close together on any galactic scale and heading in broadly similar directions. There have been serious mission concepts for something better. The Interstellar Probe study, run at the Johns Hopkins Applied Physics Laboratory over the last several years, worked out what a purpose-built successor would look like. A spacecraft launched on a trajectory designed from the outset to leave the solar system as fast as possible, carrying instruments intended for the interstellar medium rather than for Jupiter, aiming to reach 1,000 astronomical units over a mission life of 50 years. That is roughly 6 times further out than Voyager 1 is now. It has not been approved, and a 50-year mission is a difficult thing to propose to any funding body. If it were launched in the 2030s, the people who would receive most of its data have not been born. So the hum will be measured by these two machines, from the two places they happen to be, for as long as their power lasts, and then it will stop being measured, which is a strange sentence to say about a signal that is, as far as anyone can tell, permanent. The plasma of the local interstellar medium was ringing before there were instruments, and before there was a solar system, and it will be ringing long after both spacecraft are cold. The only thing that is temporary here is our ability to hear it. The hum, though, tells you about the material outside. It says almost nothing about the shape of the thing you are inside, or about how well it works. And that question, what the heliosphere actually looks like, and how much it actually protects, turned out to depend on a completely different mission, one that never left Earth orbit. 2 spacecraft, moving outward in roughly similar directions, give you 2 points. From 2 points, you cannot determine a shape. The problem is not solvable by sending more probes, because a probe takes 40 years to get there and then samples one line, so the shape of the heliosphere has to be worked out some other way, and the method that was eventually found is one of the more elegant pieces of indirect observation in modern astronomy. It rests on a process called charge exchange, which sounds technical and is not. Out in the heliosheath, you have hot, fast protons, solar wind ions that have been slowed and heated at the termination shock. You also have neutral hydrogen atoms, which have drifted in from interstellar space, uncharged and therefore unaffected by any of the magnetic fields in the way. Occasionally, one of those hot protons passes close to one of those cold neutral atoms and steals its electron. At that instant, 2 things swap. The neutral atom becomes an ion and is captured by the magnetic field and joins the plasma, and the hot proton, which was travelling fast, becomes a neutral atom and is released from the magnetic field entirely. That newly neutral atom then flies in a straight line, at whatever speed and in whatever direction it happened to have at the moment of the exchange. Nothing deflects it. It carries, in its energy and its direction, information about the conditions at the exact point in the heliosheath where it was created. Some of them fly inward, some of those reach the inner solar system. If you build a detector sensitive enough and point it at the sky, you can collect them. That is what the Interstellar Boundary Explorer was for. It launched in October of 2008 on a Pegasus rocket dropped from an aircraft into a high Earth orbit. It was a small mission. The whole spacecraft is a hexagonal drum about the size of a bus tire, and it carried essentially two instruments, both of them energetic neutral atom cameras, one for low energies and one for high. It spins, and as it spins, each camera sweeps a strip of sky, and over 6 months, as the Earth carries it around the Sun, the strips add up to a complete map of the whole sky. Before launch, several groups published predictions of what the map would look like. The models disagreed with each other about details, but they all produced broadly the same thing: a smooth, gradual variation, brighter in the direction the solar system is moving, through the interstellar medium, dimmer in the direction of the tail. A gentle gradient. The first map came out in October of 2009. Running across the sky, in a great circle, was a narrow band of emission 2 to 3 times brighter than everything around it. It was about 20 degrees wide. It went nearly all the way around. Nobody had predicted it. It was not in any of the models. It did not line up with the galactic plane, or with the Sun's equator, or with the direction of the solar system's motion, or with the ecliptic, or with anything else that was already on the map. What it did line up with, approximately, was a great circle perpendicular to the direction of the local interstellar magnetic field. The surface on which the field, draped over the outside of the heliosphere, lies perpendicular to your line of sight. The leading explanation is a 2-step version of charge exchange, and it is worth following because it says something about how the boundary works. A solar wind proton flows out to the heliosheath. It becomes neutral by stealing an electron and flies outward through the heliopause, which it can do freely because it is now neutral. Outside, in the interstellar medium, it eventually gets ionized again, and the moment it does, the interstellar magnetic field captures it, and it begins spiraling around a field line. It sits there, orbiting a magnetic field line just outside the heliosphere, for perhaps a year or two. Then it undergoes charge exchange a third time, becomes neutral again, and flies off in whatever direction its spiral had it pointing. If the field line it was spiraling around happened to be perpendicular to the direction back toward the Sun, then a large fraction of those released atoms come straight back at us. If not, they mostly go elsewhere. So the ribbon is, on this account, a reflection. It is solar wind particles that left the heliosphere, were held in the interstellar magnetic field for a year or two, and came back. The sky is showing us the shape of the magnetic field outside our own bubble, written in material that came from our own star. There is a striking piece of evidence for this. The Sun's output varies over its 11-year cycle, and the ribbon varies too, but delayed, by roughly the travel time out and back. And the delay is different at different points along the ribbon, in a pattern that tracks distance. Later work found the ribbon carrying a recognizable echo of the deep solar minimum of 2008 and 9, arriving years afterwards. The bubble is broadcasting the Sun's history back at us with a lag. This is not the only mechanism proposed, and the details are still argued over, but whatever produces it, the ribbon told everyone the same thing. The interaction between the heliosphere and the interstellar medium is dominated by magnetic field, not by simple gas pressure. And a structure dominated by magnetic field does not have to look like a raindrop. This is where Meravofa's work comes back in. The comfortable picture of the heliosphere, the one in nearly every illustration, is a comet shape. A rounded nose facing the direction of travel, and a long tail streaming out behind, because the solar system is moving through the interstellar medium at about 25 kilometers per second, and the material should pile up in front and trail behind. Magnetic fields do not behave like gas. A magnetic field under tension pulls. If the solar magnetic field inside the heliosphere is strong enough, it can pull the flanks of the bubble inward, pinching the tail into two lobes rather than letting it spread into a single trailing plume. Offa and her collaborators, modelling this with the tension of the field included, got a shape that is not a comet. It has a blunt front and two lobes behind, separated by a pinched waist. In the paper it is described as crescent-shaped. In the press coverage it became a croissant, which is unfortunate in that it sounds unserious, and fortunate in that it is genuinely the closest common object. The Voyager crossings are at minimum not inconsistent with this. Voyager 1 crossed at 121.6 astronomical units. Voyager 2 crossed at 119. Those two spacecraft are heading in substantially different directions, one well north of the plane of the planets, one well south. And if the heliosphere had a long tail and a rounded nose, you would expect the crossing distances to differ by more than 2.5 astronomical units. A blunt, compact shape fits better. Not everyone accepts it. Groups working with different assumptions about the strength and orientation of the interstellar field and about how the pickup ions behave still produce shapes with recognizable tails, though warped and asymmetric ones. There is also a complication from the Cassini spacecraft, which carried a neutral atom camera of its own and mapped a structure at higher energies that looks less like a ribbon and more like a belt, encircling the whole heliosphere, which is difficult to reconcile with the ribbon mechanism and suggests there is more than one thing going on. The honest summary is that we do not know the shape of the object we live inside. We know it is not a sphere. We know it is asymmetric. We know magnetic tension matters and probably dominates. Beyond that, there are competing models, and the data does not yet distinguish between them. And whatever shape it has, it does not hold that shape. The solar wind pressure rises and falls with the 11-year cycle. When the sun is active, the wind is stronger, and the boundary is pushed outward. When it is quiet, the boundary relaxes inward. The excursion is several astronomical units, hundreds of millions of kilometers over each cycle. That is not a small correction. Voyager 1 crossed the heliopause at 121 astronomical units in 2012. If you could go back to that exact location today, the boundary would very likely not be there. It has moved. It moves continuously. The Voyagers did not cross a fixed surface. They crossed a surface that was traveling too, and part of the reason Voyager 2 saw the termination shock 5 times in a few days is that the shock was overtaking the spacecraft and then falling back. There is one direct demonstration of this, and it did not come out of a model. In March of 2012, a large eruption occurred on the Sun. It sent a shock wave outward through the solar wind. Most such shocks weaken and dissipate long before they reach the outer solar system. This one did not. It arrived at Voyager 1, outside the heliopause, in April of 2013, 13 months later. It compressed the interstellar plasma around the spacecraft, and the compression set the plasma ringing, and that was the oscillation that Gurnet detected. The measurement that established that Voyager 1 had left the solar system was made possible by a shock wave from inside it. The Sun reached across the boundary and struck the material outside, hard enough to make it audible, from 18 billion kilometers away. Voyager has since recorded several more of these shock waves from solar events propagating out through the heliosphere, crossing the boundary and pushing into interstellar space. The last one detected before the low-energy particle instruments were switched off arrived years after the eruption that caused it. The transit is slow because the shock has to work its way through the froth of magnetic bubbles in the heliosheath, and the froth absorbs a great deal of its energy. Models had suggested the crossing should take around a year. The observed times have been considerably longer, so the boundary is a place where things pass through in both directions. Solar shocks go out, galactic cosmic rays come in, neutral atoms drift straight through as though it were not there at all, because for a neutral atom it is not. What is actually happening at the heliopause is a slow, continuous exchange, on a surface that is being pushed and pulled by both sides and never settles. As of this year, there is finally a better instrument watching it. The Interstellar Mapping and Acceleration Probe, launched in September of 2025, reached its station at the first Lagrange point, a gravitationally convenient spot about 1.5 million kilometers sunward of Earth, in January, and began its primary science mission on the 1st of February. It carries 10 instruments, including 3 neutral atom cameras rather than the Explorer's 2, spanning a much wider energy range with far better resolution. It will not go anywhere. It will sit at that point and take pictures of the boundary and escaped solar wind for at least 2 years. If the ribbon is what the reflection model says it is, the new maps should show its structure in enough detail to test the mechanism directly. If the heliosphere is pinched into lobes, that should show up in the shape of the emission at the appropriate energies. And it will be doing this while the 2 Voyagers are still out there, still reporting ground truth from 2 points inside the thing being mapped, which will be true for a few more years and then will not be true again for a very long time. Everything so far has been about the structure. What none of it addresses is the practical question underneath, which is what this bubble is actually for, and how much difference it makes that we happen to be inside it. Galactic cosmic rays are not rays. The name is a 19th century misunderstanding that stuck. They are atomic nuclei, about 90% bare protons, about 9% helium nuclei, and a remainder of heavier elements up to iron and beyond travelling at very close to the speed of light. Their energies are difficult to convey without reaching for a comparison, so I will use one and then stop. A typical galactic cosmic ray carries about 1 billion electron volts. The most energetic ones ever detected carry more than 100 million times that a single atomic nucleus arriving with the kinetic energy of a well-struck tennis ball. Those are vanishingly rare. The ones that matter for what follows are the ordinary ones, in the range from a few million to a few billion electron volts, which arrive constantly and from every direction. Where they come from was argued about for most of the 20th century, and the answer is largely settled now. The bulk of them are accelerated at the shock fronts of supernova remnants by a process in which a charged particle bounces repeatedly across the shock, gaining a little energy on each crossing, in the same way a ball gains speed when batted between 2 approaching walls. The mechanism has a name: diffusive shock acceleration, and it naturally produces the power law energy distribution that is observed. The confirmation came in 2013 from the Fermi Space Telescope. Looking at 2 middle-aged supernova remnants, it found a specific spectral feature in their gamma-ray emission: the signature of neutral pions decaying. Neutral pions are produced when cosmic ray protons collide with ordinary protons. Finding the decay signature meant finding protons being accelerated there, rather than only electrons, which had always been the ambiguity. Supernova remnants make cosmic rays. Those particles then wander the galaxy, spiraling along magnetic field lines for something like 10 to 20 million years before escaping or being absorbed. By the time they arrive here, they have lost all memory of where they came from. Their directions are effectively random, because the galactic magnetic field has scrambled them, and then they hit the heliosphere. The heliosphere reduces the number of them that get in. It does this because a charged particle trying to cross an outward-flowing magnetized plasma has to work against it. The field is convected outward with the wind, and the particle has to diffuse inward against that flow, scattering off irregularities and losing energy as it does so. The effect is strongly dependent on energy. The most energetic cosmic rays pass through almost unaffected. The low-energy ones are largely excluded. This is called solar modulation, and it is directly observable from the ground. Neutron monitors, instruments that count the secondary particles produced when cosmic rays hit the atmosphere, have been operating continuously since the 1950s. Their counts go up and down over an 11-year cycle, and they do it out of phase with the Sun. When the Sun is most active, the count is lowest. When the Sun is quiet, cosmic ray intensity at Earth rises. Here is the problem that made Voyager necessary. Because the low-energy end of the cosmic ray spectrum is exactly the part that the heliosphere removes, nobody had ever measured it. Every instrument that had ever counted cosmic rays was inside the shield. What the actual interstellar spectrum looked like below about 1 billion electron volts was an extrapolation, and different extrapolations disagreed by large factors, and there was no way to check. Voyager 1's cosmic ray subsystem, 3 telescopes built at Caltech and Goddard, under Ed Stone, went outside the shield in 2012 and measured it. The total intensity of galactic cosmic rays roughly doubled after the crossing. That is the headline number, and it is the one usually quoted. The heliosphere blocks about half of them. The more useful result is the shape. Below a few 100 million electron volts, the interstellar spectrum turned out to be far richer than most models had assumed. A substantial population of low-energy particles that never reached the inner solar system at all, and that had been essentially invisible. That measurement is now the anchor point for calculating cosmic ray effects throughout the galaxy, for working out the ionization rate of interstellar clouds, which controls how they collapse to form stars, and for calibrating how much heating cosmic rays supply to gas that would otherwise be colder. One spacecraft, one instrument, one measurement, and a parameter that appears in a great deal of galactic astrophysics went from an extrapolation to a number. Now, what does the shield do for us? Less than you might assume at the surface of the Earth, because the Earth has two better ones. The planetary magnetic field deflects a substantial fraction of the arriving flux, particularly at low latitudes. And the atmosphere is the real defense. 10 tons of air above every square meter, equivalent in shielding to about 10 meters of water. A cosmic ray striking the top of it produces a cascade of secondary particles, and by sea level, most of what reaches you is muons. The dose is real, but small cosmic radiation contributes a modest fraction of natural background exposure, and it roughly doubles for every 2 kilometers of altitude, which is why aircrew accumulate measurably more than people on the ground. Outside the atmosphere, it is a different problem entirely. The radiation detector aboard the Curiosity rover measured the dose during its cruise to Mars, and the figures from that measurement have shaped mission planning ever since. A round trip to Mars, with realistic shielding and time on the surface, delivers a cumulative dose that pushes an astronaut close to career exposure limits, with most of it coming from galactic cosmic rays rather than from the Sun. Solar particle events are more intense, but you can shelter from them for a few days. Cosmic rays are always there, and heavy nuclei among them are difficult to shield against, because stopping them in a wall generates secondary particles that can be worse than what you started with. So the heliosphere is not what protects your body when you are standing outdoors. It is what determines the radiation environment of everything in the solar system that is not under an atmosphere. The question that follows naturally is what happens if it weakens, and this is where I want to be careful, because it is an area where honest uncertainty gets replaced by confident storytelling very easily. Here is what is well supported. The size of the heliosphere depends on the pressure balance between the solar wind and the surrounding interstellar material. The Sun's output varies, and so the boundary breathes on an 11-year cycle by several astronomical units. Over much longer periods, the Sun's activity varies more. There have been extended quiet periods, like the 17th century Maunder minimum, during which cosmic ray intensity at Earth rose measurably. We know that last part because cosmic rays leave a record. When they strike the atmosphere, they produce, among other things, carbon-14 and beryllium-10. Carbon-14 is taken up by plants and locked into tree rings, 1 ring per year, going back thousands of years. Beryllium-10 settles onto ice sheets and is preserved in layers. Both give year-by-year records of how many cosmic rays were arriving, and both show the 11-year cycle, and both show the long quiet periods, and both were how the Maunder minimum was confirmed independently of the historical sunspot drawings. That record has also caught things nobody expected. In 2012, a Japanese researcher named Fusa Miyake found a sharp spike in carbon-14 in Japanese cedar rings, dated to the years 774 and 775. It was found afterwards in tree rings worldwide, and in beryllium-10 in ice cores, confirming it was a real global event. The cause is most likely an enormous solar particle event, far larger than anything in the instrumental record. Several more such events have since been identified at other dates. They are now used as absolute calendar markers in archaeology, because a single ring anywhere in the world can be pinned to a known year. That is the well-supported part. Cosmic ray flux at Earth varies. We can read the variation, and the variation is driven by solar activity, and therefore by the state of the heliosphere. Here is the part that is not settled, whether that variation matters to anything on the ground. There is a hypothesis, associated most strongly with the Danish physicist Henrik Svensmark, that cosmic rays influence cloud formation by ionizing the atmosphere and seeding the aerosol particles on which cloud droplets condense, and therefore that variations in cosmic ray flux drive variations in cloudiness, and hence in climate. It is a physically plausible chain. Each link exists. It has been tested carefully. An experiment at the European Particle Physics Laboratory near Geneva was built specifically to examine it, using a beam from a particle accelerator to simulate cosmic ray ionization in a chamber of ultra-clean air. It found that ionization does enhance the nucleation of aerosol particles under some conditions. It also found that the effect on the number of particles that actually grow large enough to seed cloud droplets is small, and that over the range of cosmic ray variation the solar cycle actually produces, the resulting change in cloud cover is far too small to account for observed climate variation. The current position among most people working on it is that the mechanism is real and the magnitude is insufficient. That is not the same as saying nothing happens. It is saying that the effect measured so far is too small to matter at the level claimed. I mention it because the alternative, skipping it or presenting it as settled in either direction, would be dishonest about where the science is. What is not in dispute is that the heliosphere has not always been this size and will not stay this size, and that the reason is not the sun, it is the neighbourhood. The pressure on the outside of the bubble is set by whatever interstellar material the solar system currently happens to be moving through, and the solar system has been moving for 4.5 billion years. And it does not always move through the same thing. The sun is moving in several ways at once, and it is worth separating them. It orbits the centre of the galaxy at about 230 kilometers per second, completing one circuit in something like 230 million years. The last time it was in this part of its orbit, the first dinosaurs were appearing. In addition, it drifts relative to the average motion of the stars around it, about 20 kilometers per second, toward a point in the constellation Hercules, and it bobs, oscillating up and down through the plane of the galactic disk every 60 or 70 million years, like a horse on a carousel. The consequence of all that motion is that the solar system does not stay in one environment. It travels through the interstellar medium, and the interstellar medium is not uniform, and so the conditions at the outer edge of the heliosphere change over geological time. Right now, we are in a very thin place. The immediate neighbourhood is a wisp of warm, partly ionized gas called the local interstellar cloud, or in the informal name that has survived because it is better, the local fluff. It is roughly 30 light-years across. Its density is around 1/10 to 1/3 of an atom per cubic centimetre. Its temperature is about 7,500 Kelvin, which sounds violent and is not, because temperature in a gas that thin describes how fast the individual particles move and says nothing about how much heat there is to transfer. A hand held in it would freeze, not burn, because there would be almost nothing to conduct heat into it, and it would radiate its own warmth away. The cloud is moving relative to the sun at about 26 kilometers per second, which means that from our point of view we are flying into a headwind. That headwind is what compresses the heliosphere on the leading side and stretches it behind. We entered the cloud somewhere between 50 and 150,000 years ago. The number is uncertain because it depends on the cloud's boundary, which is not sharp. We will leave it within a few tens of thousands of years. Recent work suggests the sun may in fact be very near the cloud's edge already, close to a boundary with a neighbouring structure known as the G cloud, which is denser, and the local interstellar cloud is itself sitting inside something much larger and much emptier. The local bubble is a cavity in the interstellar medium, and the modern picture of it comes almost entirely from Gaia, the European space telescope that measured precise distances to more than 1 billion stars. With those distances, and with measurements of how much starlight is dimmed by intervening dust, it became possible to build a genuine three-dimensional map of the dust within a few thousand light-years, not a projection on the sky, but a model of where the material actually is. That map, published in 2022 by Catherine Zucker and colleagues, shows the sun sitting near the middle of a roughly spherical hole about 1,000 light-years across, almost entirely free of dust, with a shell of swept-up material around its inside surface. The reconstruction of how it formed is specific. Around 14 million years ago, a group of massive stars began exploding. The analysis suggests something like 15 supernovae over that period, and their combined shock waves cleared a cavity, pushing the gas and dust outward into a dense shell. That shell is where the nearest star-forming regions now are: Taurus, Ophiuchus, Lupus, Chamaeleon, Corona Australis. Nearly all of the nearby regions where new stars are currently condensing sit on the surface of that bubble, and they are there because the material they are made of was piled up by those explosions. The sun had nothing to do with it. We drifted into this cavity roughly 5 million years ago and happen to be near the center of it now, by coincidence. There is physical evidence on this planet that we passed close to at least some of those explosions, and it is one of the more unlikely pieces of evidence in the whole of astronomy. The isotope iron-60 is radioactive, with a half-life of about 2.5 million years. That is short enough that essentially none of the iron-60 present when the Earth formed can still exist. Any that is found now must have arrived recently, and it is not produced in any significant quantity by ordinary processes on Earth. It is made in massive stars and dispersed by supernovae. Iron-60 has been found in ferromanganese crusts from the deep ocean floor, in deep-sea sediments from several ocean basins, in lunar soil returned by Apollo, and in Antarctic snow. The deep-sea record shows a clear peak deposited around 2 to 3 million years ago, and a second, older one, around 6 to 8 million years ago. The interpretation is that supernovae occurred within a few hundred light-years of the Sun at those times, and that the debris eventually reached us and settled through the atmosphere and into the seabed and stayed there. The Antarctic snow result is not about the past. Iron-60 is being deposited now, not 2 million years ago, currently, which suggests the solar system is still moving through material enriched by those explosions. We are inside the debris. It is landing on the ice. What that debris did to the heliosphere at the time is harder to establish, and there is an active argument about it. In 2024, Meravofa and collaborators published a model proposing that around 2 million years ago, the solar system passed through a cold, dense cloud of the kind found in the local ribbon of cold clouds, and that the pressure of that encounter could have compressed the heliosphere dramatically down from 120 astronomical units to a small fraction of that, potentially inside the orbit of the Earth. If that happened, the planets would have been outside the heliosphere entirely, sitting directly in interstellar material for anything from a few centuries to a million years. It is a model, it is contested, and the timing overlaps awkwardly with the Iron-60 peaks in a way that different groups read differently. But it is a serious proposal in a refereed journal, and what it implies is worth sitting with. The protective bubble is not guaranteed. It exists because of a pressure balance, and one side of that balance is set by whatever the solar system happens to be passing through. Looking forward, the near-term picture is undramatic. When the Sun leaves the local interstellar cloud in some tens of thousands of years and enters the somewhat denser G cloud, the external pressure will rise and the heliopause will move inward. The estimates are for a contraction of some tens of astronomical units, not a collapse. The cosmic ray flux in the inner solar system would rise correspondingly. The Earth's atmosphere and magnetic field would continue doing the bulk of the shielding they do now. It would take centuries to millennia to happen, and there is no obvious mechanism by which anyone would notice it directly. On the longer timescale, the solar system will eventually leave the local bubble altogether and pass into ordinary galactic material, and at some point cross a spiral arm where the density is higher and supernovae are more frequent. It has done this many times. There is no record of the heliosphere from those crossings, and there may never be one, because the heliosphere leaves no fossils. There is one more thing worth saying about the material out there, and it is not about danger. Among the cosmic rays that Voyager's detectors counted before they were switched off were nuclei of iron, nickel, and other heavy elements. Those cannot be made in the Sun. Fusion in a star like ours stops long before iron. Those nuclei were assembled inside stars considerably more massive than the Sun in the last stages of their lives, and were thrown out when those stars collapsed, and have been travelling and scattering through magnetic fields ever since for millions of years, possibly for far longer. Every one of them that struck a detector on Voyager was a fragment of a star that died before the Sun existed, and the same material, in vastly greater quantity, is in the ground under your house and in the hemoglobin currently moving through your arm. The reason I put those two sentences next to each other is not to make a point about our connection to the cosmos. It is because until 2012, that material had never been measured at its source. It had been inferred from spectroscopy and from theory, and the inference was correct in outline. But nobody had ever put an instrument into the medium itself and counted what was there. Two machines built in the 1970s did that. They are still doing it, with two instruments each and falling power, in a place nothing else has reached, and they will be finished within about a decade. It is worth being precise about what is still open, because the list is longer than the coverage usually suggests, and because the open items are not vague. They are specific numbers that do not add up. Start with the one that has bothered people the longest, which is pressure. The heliopause sits where the pressure inside equals the pressure outside. That is the definition. So if you measure the pressure inside and you measure the pressure outside, they should match. Voyager 2, with a working plasma instrument, measured the inside. The outside is estimated from the density, the temperature, and the magnetic field of the local interstellar medium, all of which are now measured reasonably well. They do not match. The pressure the spacecraft could account for inside the heliosheath, from the thermal protons and electrons it could see, falls well short of what is needed to hold the boundary where the boundary is. Something is supplying the difference. The favoured answer is the pickup ions again, the interstellar atoms that drifted in, got ionized, and were swept up. They are few in number and enormously energetic, and they can carry most of the pressure while carrying almost none of the particles. The instruments on Voyager cannot properly measure them. Their energies fall awkwardly between what the plasma instrument sees and what the particle instruments see. So the leading explanation for the missing pressure is a population that neither spacecraft can adequately observe. That is an uncomfortable position for a field to be in. The dominant pressure component in the outer heliosphere is the one thing we did not bring an instrument for. Second, the magnetic field just outside the heliopause is stronger than it should be. Estimates of the local interstellar magnetic field, derived from the shape of the heliosphere and from the geometry of the ribbon, put it at a few tenths of a nanotesla, very weak by terrestrial standards, roughly 10,000 times weaker than the field at the Earth's surface. Voyager 1, after crossing, measured a field of around 4 to 5 tenths of a nanotesla, which is at the high end, and Voyager 2 measured something comparable. That is stronger than most models wanted, and it means the region just outside the heliopause is magnetically dominated. The magnetic pressure there exceeds the thermal pressure of the gas. Whether that reflects the general local interstellar field, or whether it is a pileup specific to the region immediately outside the bubble where the field is draped and compressed, is not resolved. The two spacecraft are both in the pileup, if there is one, and neither is far enough out to escape it and measure the undisturbed field beyond. Third, the direction of that field does not agree with itself. The interstellar magnetic field direction can be inferred two ways. One is from the ribbon, which is believed to trace the surface where the field is perpendicular to the line of sight, and which therefore implies a specific field orientation. The other is from the Voyager magnetometers, measuring it directly at 2 points outside the heliopause. The two answers differ, not enormously, but by more than the uncertainties comfortably allow a difference of the order of 20 degrees, depending on whose analysis you take. Either the ribbon mechanism is not quite what it is thought to be, or the field near the heliopause is bent enough that a local measurement does not tell you the global direction, or both. The Interstellar Mapping and Acceleration Probe was built partly to address this. Fourth, the density outside keeps rising, and nobody is certain why. The continuous measurement from the hum shows the electron density around Voyager 1, climbing steadily as it moves outward from around a 20th of an electron per cubic centimetre, shortly after the crossing to above a tenth more. Recently, there is a gradient, and it is sustained over tens of astronomical units. There are several candidate explanations. The spacecraft may be moving out of a compressed layer close to the heliopause and into the undisturbed medium, in which case the rise will level off. It may be moving into genuinely denser material within the local interstellar cloud, in which case it will not. It may be seeing structure in the cloud at scales that no other technique can reach. All three are plausible. The way to distinguish between them is to keep measuring, and the ability to keep measuring is limited by a plutonium supply that is half gone. Fifth, the acceleration site of anomalous cosmic rays, which was the clean prediction that failed at the termination shock in 2004, is still not confidently identified more than 20 years later. The best current thinking places it along the flanks of the shock, where the magnetic field is oriented more favourably, but nothing has been there to check. And sixth, most fundamentally, the shape. Everything that has been said about the heliosphere's asymmetry rests on two crossings, in two directions, plus a map made in escaped particles. There is no direct information at all about the tail, whether it is long or split into two lobes, or effectively absent. There is no direct information about the flanks. Nothing has ever measured the boundary anywhere, except in the two narrow directions where the Voyagers happened to go, and those two directions were determined in 1977 by the requirements of a Jupiter and Saturn flyby. I want to be clear that none of this is a failure. This is what the front edge of a subject looks like when you get close enough to see it. 15 years ago, most of these questions could not have been asked in this form, because the measurements that make them sharp did not exist. The pressure problem is a real problem precisely because somebody measured the pressure. The field direction disagreement exists because there are now two independent ways of determining it, and having two ways that disagree is a much better position than having one way that nobody can check. But it does mean something particular about timing. There are two working instruments on Voyager 1 and 3 on Voyager 2. The power falls by 4 watts a year and cannot be replenished. The team is currently attempting a substantial rearrangement of the spacecraft's electrical systems specifically to buy a few more years. Even if everything goes well, the realistic ceiling is somewhere in the early 2030s, and after that the transmitters will not have the power to be heard. There is no replacement in flight. The interstellar mapping and acceleration probe is at the first Lagrange point, 1.5 million kilometers from Earth, imaging the boundary from the inside. It is an excellent instrument, and it is not a probe of the interstellar medium. The interstellar probe concept, which would be, has not been approved, and if it were approved and launched in the 2030s, it would not reach the heliopause until around 2060. So the direct record of the local interstellar medium is going to consist of what these two machines report between now and roughly 2032, and then it is going to stop, and there is going to be a gap of decades at minimum. Everything in this list will still be open when that happens. The end of the mission will not be an event either. It will happen the way everything else on this mission has happened, which is gradually and by decision. An instrument will be switched off to save 4 watts. Then, a year or two later, another one. At some point there will be one science instrument left, and then there will be none. And the spacecraft will continue transmitting engineering telemetry for a while, because that costs less power than science does. Then the power will fall below what the transmitter needs to produce a signal. The deep space network can separate from the noise, and a pass will be scheduled, and the antenna at Canberra or Goldstone or Madrid will listen at the appointed hour, and there will be nothing there. It is likely that nobody will know the exact moment. The spacecraft is not going to announce it. There will simply be a last successful contact, and then a series of unsuccessful ones, and at some point, somebody will have to decide how many failed passes constitute an ending. After that, the objects continue. Nothing stops Voyager. There is no drag. The material it is moving through is thin enough that the collisions are negligible on any timescale that matters. The sun's gravity is still acting on it, and still slowing it, but the spacecraft is well above escape velocity, and the sun's grip weakens with the square of the distance. Voyager 1 is leaving at about 17 kilometers per second, and it will still be doing something close to 17 kilometers per second in 1 million years. So both spacecraft will become what they were always going to become. 2 more objects in orbit around the center of the galaxy, on paths determined by where they were when the sun let go of them. They will circle the galactic center roughly once every 230 million years, alongside the sun and every other star in this part of the disk, slowly drifting apart from all of it. The individual encounters are almost meaningless, and I will give them anyway, because they are the only landmarks available. In about 40,000 years, Voyager 1 will pass within roughly 1.5 light-years of a small red star in Camelopardalis, catalogued as Gliese 445. Around the same time, Voyager 2 will pass within a similar distance of Ross 248. In Andromeda, neither is an encounter in any useful sense. 1.5 light-years is 14 trillion kilometers. If there were a planet around either star, the spacecraft would not be detectable from it by any means. Nothing will happen, and they will not erode. This is the detail that changes the scale of the thing. There is no oxygen to corrode them, no water, no weather, no biology, and no meaningful abrasion. The estimates for micrometeoroid erosion of the Golden Record, which is protected by its aluminium cover, come out at something like a fraction of a millimeter over hundreds of millions of years. Cosmic ray damage will slowly disorder the crystal structure of the metals. The plutonium will decay to lead. The hydrazine will freeze and stay frozen. But the shape will remain, and the grooves in the record will remain, and the diagrams etched on the cover will remain essentially unchanged for something on the order of 1 billion years. That is longer than the Earth will remain habitable. The sun brightens by about 1% every 100 million years, and the usual estimates put the end of complex life on this planet somewhere between 600 million and 1.5 billion years from now, from heating alone, long before the sun becomes a red giant. Voyager will still be recognizably Voyager after that. The uranium sample on the cover of the record, plated there as a clock, will have gone through perhaps a fifth of one half-life. There is a diagram on that cover showing the position of the sun relative to 14 pulsars, each labelled with its rotation period in binary. Pulsars slow down at rates that are precisely known. The map is therefore also a date stamp. Anything that understood pulsars could measure their current periods, compare them to the ones etched on the cover, and determine when the object was launched. Frank Drake designed it that way deliberately. It works in both directions, and it will keep working for as long as those particular pulsars keep spinning. I do not think any of that is likely to matter to anyone. Carl Sagan said as much at the time, and he was not being modest about it. The probability of the record ever being found by anything is essentially zero, and everyone involved understood that when they made it. What it does is fix a date. There was a period, lasting a few decades in the middle of the 20th century, when a species that had only recently learned to leave its atmosphere built two machines and threw them out of its solar system and put a record on the side of each one, because it seemed like the right thing to do. That period ended. The machines did not. Let me come back to where this started. On the 18th of November this year, at around 2:15 in the morning, Pacific time, Voyager 1 will be one light day from Earth. One full rotation of this planet's worth of distance, measured in the fastest thing there is. A signal leaving the spacecraft at that moment would arrive here a day later, having crossed 25.5 billion kilometers without meeting anything substantial enough to slow it down. It is a milestone with no physical significance whatsoever. Nothing changes at that distance. The spacecraft will not notice. It is simply a number that becomes true at a specific minute, calculated in advance by people who wanted to know, and it is the last such milestone anyone is going to be present for. The machine that reaches it left the ground in 1977, carrying a computer with 69 kilobytes of memory and a radio the strength of a refrigerator bulb. It was built for 5 years. It found volcanoes on a moon that was supposed to be dead, and rings around planets that were not supposed to have them, and then it went out past everything, and discovered that the edge of the sun's territory is not a line, but a thick, moving, leaking layer of magnetic foam, that the space beyond it is 40 times denser than we had calculated, and that the material out there is not silent but produces a faint continuous tone at 3 kHz that nobody has fully explained. 2 instruments on it are still working. They will be switched off within a few years, and after that the machine will keep going anyway, out through the wall of the local bubble and into the general body of the galaxy, at 17 kilometers per second, in a straight line, indefinitely. The last thing it will do while anyone is listening is measure the density of the gas around it, and report the number, and wait 23 hours for an answer. Good night.